there were two main drivers of the transition for West Mercia Police. There's a recognition that reducing carbon emissions will be beneficial for the communities that they serve, and also the impact of the zero emission vehicle mandate on procurement. Having a comprehensive transition plan to work from is going to be key to achieve their goals of halving 2023 emissions by 2030 and it being fully net zero by 2050. Fleet emissions are very significant. They actually account for almost half of the force's Scope 1 and Scope 2 emissions. The fleet can be thought of as being composed of many subfleets, and each has very different vehicle specifications and duty cycle requirements. So the non-response vehicles are simpler to electrify, but significant numbers of response vehicles have high performance duty cycles and include very high driving speeds, heavy payloads, and short charging windows, and this can present quite a unique challenge. The primary concern was, are EV battery capacities able to support the intense energy demand in these vehicles? To model the fleet, FPS took historic telematics data and converted this into duty cycles, which we applied energy models to, which were derived from the wider work in Project Response. And this was used to understand the equivalent EV energy consumption. By assessing the available charging windows of the vehicles, we were able to derive how many of the duty cycles would be feasible without en route charging, how many chargers of what type would be required at each site, and the utilization and charge profiles of those chargers. As you might expect, there is a wide range of charging needs across the fleet, and that is reflected in the site infrastructure requirements. Using the historic vehicle movements and dwell times as they are, one charger was needed for roughly every 2.3 vehicles, and DC chargers were needed at most sites. However, the majority of these DC chargers, they would only be used maybe once a day or less, which indicates that they might not actually be needed for the operational requirements, as driving behavior and dwell times will change once EVs are embedded in the fleet. This can be a limitation of using historic diesel driving behavior to model EVs, and always needs bearing in mind when looking at and assessing the outputs of any modeling. Eliminating those chargers would mean that one charger is needed for every 3 vehicles, and less than a third of sites need a DC rapid charger. Obviously, this needs to be confirmed through trials, but would result in a very large cost in savings. The 49% is based on the number of vehicles which would have required no en route charging using on-the-market EVs over the study period. This is a pretty strict criteria, as it doesn't take into account that when vehicles are electrified, driving patterns are likely to change. So to unlock the remaining 51% of the fleet, a combination of advances in EV technology, as well as EV pilot deployments in the fleet, will be needed. Based on the current rate of EV range increases, we predict that by 2030, it will be possible to electrify 97% of the fleet and the remaining 3% by 2035. We identified the £1 million in potential infrastructure cost savings by assessing which of the DC rapid chargers needed to make the historic duties work were actually used less than once a day. And that can indicate that the primary driver behind their requirement isn't operational, such as vehicles regularly needing to respond to another call out with very short turnarounds, but actually more likely to be caused by driving behaviors of diesel vehicles. And after dropping those low utilization charges, DC chargers were still required at sites with the types of vehicles that have high performance requirements and high blue light utilization, but at other sites were flagged as unlikely to be required. The first recommended step was to form a cross-functional working group. This can make it much easier to select pilot sites and vehicles, and also create a timeline for carrying out the necessary site surveys for things like cable runs and charger placement. Once that's done, engaging DNOs for power upgrades will make it easier to build a phased rollout map. Finally, but potentially most importantly, pilots should be used to test things like charger prioritization rules and EV driver behaviors through data collection from vehicles and chargers. The core approach is likely to be highly transferable, as the same data sets tend to be available, and these fleets tend to have a range of sub-fleets performing very different roles and duty cycles. Details will always need fine-tuning, as every organization and geography is different.